So last class, remember, we basically finished up talking about memory management. So just to give people, a reminder sort of where we came since we started talking about memory. Remember, we started with, doing very simple ways of allocating memory to processes, contiguous allocation. And then we ran into problems like, limited physical memory and internal and external fragmentation. So from there, we moved on to, using paging and segmentation that allows us to get around a lot of these issues. And of course, there, the big challenges are things like how to do this efficiently and how to translate virtual to physical addresses, often with some kind of hardware support. And then last class, we finished up talking about page replacement algorithms. In particular, LRU is sort of the algorithm we'd like to get close to. And so we talked about, the second chance algorithm and the enhanced second chance algorithm as a way that we can approximate that. And then we finally talked about considerations when we're doing multi-programming, and we largely want to avoid thrashing regardless of how much physical memory we have and how many processes we're trying to run. So that's pretty much it for memory management. So today we're going to start talking about the third major topic, which is file systems. So first, to just sort of give us a frame of reference, remember that we're talking about the OS, largely as some kind of a translator, where we're basically being given an abstraction to the hardware. Remember, so we have been talking about memory. Now we're going to start talking about I/O devices. Now, of course, there are lots of different types of I/O devices your computer might have. The most common one is a disk, so that's going to be the one we're focusing on. So the abstraction that the OS is going to be giving us that we can work with is going to be files when we're talking about disks. So actually, first, just sort of start us off. Files. We all sort of have some intuitive sense of what files are, but somebody tell me what do you think a good definition of a file is? What is a file? Right. We all use files all day long. So what is a file? Right, because it's sort of not an answer that sort of is an obvious, there isn't really sort of an obvious answer, because the notion of a file is just sort of a nice, convenient abstraction. Right, so all essentially a file is it's some collection of logically related data that we've given some name. Right, ultimately a file is just some, bit sitting on a hard disk somewhere, most likely. It could be on some other type of device, but most likely a hard disk. And it's just some logical piece of data that we've given a name. Right, but the notion of a file is just a nice, convenient abstraction that the OS is giving to us. So we're basically going to be talking about, what are the details that actually go into how an OS, provides that kind of abstraction to us. So the picture we can kind of keep in our head is something like this. Right, so again, down here at the bottom, we're going to have our physical hardware, whatever the type of I/O device it is, and for the moment, we'll basically just assume we're talking about a regular, hard disk, but you could have other, things like a network device, for example. And basically, there's an interface to the hardware itself, which is basically provided by a piece of code in your kernel called a device driver. Right, so you may have lots of different types of I/O devices that all need to be, talked to in a certain way. They all have their own behavior. So you basically have a device driver in your kernel for every type of device you want to be able to talk to. So the device driver is talking, directly to the disk. And a hard disk has these notion of things like sectors and tracks, which we'll talk about. But essentially, those are all disk-specific notions. Now, sitting on top of that, we're basically going to have a device-independent interface that's sort of not going to worry about the exact details of the underlying I/O device. Right? Because in general, what we're doing with all these various types of devices is things like opening and closing files and reading and writing files. Right? And so that notion sort of stays the same regardless of if we're talking about a hard disk or a CD or a network device or whatnot. So now for disks, we're actually going to have another level of abstraction up to our actual programs, which is the file system itself. Right? Because when you are issuing calls from an application, everything is going through the file system, which itself is an abstraction that is actually going to be issuing things like reads and writes to data on your hard disk. So those calls are filtered through your file system, which is then going to be talking all the way down to your device driver, which is actually going to be reading and writing the disk. So let's talk about sort of what our requirements are when we're talking about file systems and dealing with data on I/O devices, right? So the big difference we have here from when we were talking about memory is, or at least one of the big differences, is persistence, right? So in memory, sort of everything is very temporary, right? If you shut off your machine or your machine loses power, everything in memory is gone. Right, so the big difference here on disk is that we have persistence. Even if you lose power or your application crashes or you have to restart your process, everything on disk in general is still going to be there. Now, another difference is we of course still want to be able to access data on a disk quickly. Now, of course, we've already talked about this some. Disk is going to be much, much slower than memory, but we still want to be able to access disk reasonably quickly because that's still an operation we're going to be doing a lot. Now, of course, also on disk, sort of the scales of size are much different. On memory, we're sort of very worried about, well, how much data can I actually store in memory, and what can I do to get around the fact that often I'm going to want more than I actually have. In disk, with a disk, that's not really an issue. You might have a terabyte of disk storage, and if you need more, pretty easy, you can just go out and buy another disk. Not that expensive, not difficult. So sort of the amount of storage you have is much less of a consideration. Other things we need to deal with are things like sharing and protection, right? So you're still going to have data on your disk that you might like to share between users or explicitly not share, so we want to be able to provide that. And then finally, ease of use. Right, so the file system itself is basically an abstraction that is designed to be easy to use. Right, so the simplest way in which a file system is easy to use is that all of your files have these nice human readable names. Right, so you name your file something, and that makes it easy to find the data that you're looking for that's stored on your disk. Now that's sort of the most simple example, but there are also other ways in which you would like your data to be easy to use. Right, so you may have tens of thousands of files on your machine. They may all have nice names, but when you look for something on your computer, oftentimes you're not going through a list of 10,000 files and looking for the right name. You're going to be doing something like using your search function built into your OS. Right, that's going to be searching your file system. Right, so that's another example of a facility that makes it easy to find information that you have stored on your disk. So we also want to be able to provide that sort of thing. So all these various requirements are going to sort of be split between what the actual hardware is going to provide us and what the actual software of the OS is going to provide us. Right? So for example, persistence, obviously part of that is simply the physical properties of a disk. Right? Because memory, when it loses power, essentially loses all state. A disk is basically magnetic storage that doesn't need power to maintain the state that it has. So, hardware is basically providing persistence in that way. Now, our disks are basically designed to be random access, meaning you can essentially access any part of the disk you want at once. So that's going to help in allowing us to access data quickly. And of course, disks just physically have been getting very, very large and very inexpensive. So that's also giving us the size. Now, on the OS side of things, there's still some issues in persistence. Right, so you may have encountered, for example, your machine loses power and maybe a file you were working on gets corrupted. Right, that could still be something that happens, so you could design your OS, and some file systems do have functionality that basically are designed to do some kind of recovery. So the OS can still be involved in providing persistence. Now, something like sharing and protection is something that's largely provided entirely by the OS. Right, so your files are going to have certain permissions set that determine who can read and write them. That, of course, is something that essentially just your OS is providing. And then, all the various pieces of ease of use, things that we already mentioned, things like, associating names with your files is obviously something the OS is providing you. And, things like organizing files into directories and providing search functionalities, those are all also provided by the OS. Questions on this before we move on? This is just sort of the high level of what we're looking for in our file systems. Okay, so let's start talking about files. right? So we already said earlier that basically a file is just some logical unit of data that's sitting on some storage device, which in general we can assume is going to be a disk. And so, anything basically on your disk with a name is, of course, a file. So we're all using files every day. You save information in files, you open up files, programs are saved as files, right? Pretty much all the data that is permanently, reasonably permanently on your disk is stored in a file. Now, files can contain, all different types of data, right? You can have textual files, you can have binary files, you could have, files that are executable code, right? So a program stored in binary form on your computer is a file. Now, of course, if you try to, open that up in a text editor, it's going to look like, complete garbage because it's not textual data designed to be seen. It's basically just machine code. And so, all different things that you can have in a file. And files can also be basically structured or unstructured, which essentially refers to, does the OS itself actually know anything about what your files are containing? And so there's essentially two approaches here. The unstructured approach is basically what a system like Unix does, which is a file is a bunch of bytes on disk, and there's essentially no further organization imposed by the OS on how the file is laid out. It's essentially just arbitrary data, and it's up to a program to actually take that data and do something with it. Versus a structured approach is where you're going to actually lay out your files with some imposed organization, like a series of records or objects. And so there, the OS is actually sort of taking a more active role in how your files are actually laid out and what the data actually is. Now, of course, when we think of a file, we normally think of a file with some name, right? Because you give all of your files a human-readable name. But ultimately, from the OS's point of view, the name is just a convenient piece of data that it shows you, but essentially a file is just represented by some unique identifier, typically just some integer. Right? So again, the name itself is basically just a convenience for the user, and there's some other actual identifier being used. And then there's lots of other different types of attributes that are typically associated with a file. And all of this is usually called metadata. So lots of different types of metadata. Obviously, the name is one example. The type of the file. Is it an executable program? Is it a text document? Whatnot? That would be an example of metadata. Where it's stored on your disk, how large it is. Who is allowed to access it. What's its creation time. These are all examples of metadata. So just to give sort of a simple example, if I have some, where's my cursor? There it is. If I have some file here, these are lecture notes from last class, then I can get info on this, and this is basically just showing all of the, or at least a good part of the metadata associated with this particular file, right? So there's some name, it has. This is saying, what program created it, when was it opened, when was it created, all these types of things are basically just being stored with that file. So let's talk about what the common operations on files are. Right, so we have operations that are basically doing things to the data itself of the file, and then we have operations that are working basically on the file metadata. Right, so when we're actually dealing with the data of the file, that's when we're doing things like opening a file and then reading and writing it. When we seek, that's basically saying when we are moving to a certain position in the file. So oftentimes the way we're basically doing file I/O is, if you imagine your file's data is just a bunch of bytes, you basically have a file pointer that's pointing somewhere in the file. Let's say the file pointer is pointing here. And when you're basically saying read, you're saying read forward from this file pointer. So maybe we call read and we read that block. But now maybe we want to read something over here. So the first thing we might do is we might call seek, which is basically just going to move this file pointer over here. And now we can call read or write and act on data over here. Right, so seek is basically just updating where a file pointer is pointing in a file when you're working with it. And then lots of different operations on the actual metadata of a file, things like updating who owns a file, who's allowed to access it, and things like hard links and soft links, which we'll talk a little bit more about in a minute. So basically, all of these are basically provided as system calls, and those are what your programs are actually calling in order to work with files. Those are all and again, you're not normally calling these system calls directly, right? As we've seen before, these things are normally contained in some software library that you're working with, right? So if you're using something like a C library, you're usually calling things like fopen and fwrite, which are going to be using open and write underneath, but are essentially library wrappers for the actual system calls you're using, right? So this is the same idea we saw a while ago when we were talking about things like fork. So let's talk about what the data structures are that the OS is providing. So basically, there are two main data structures to keep in mind. So first, there's essentially a global table of open files, meaning files that a process is currently working with, right? So when a process wants to work with a file, the first thing it generally has to do is open the file, and then it can do things like read and write to the file. So there's essentially one big table that's shared by all processes that has all the files that are currently open. And so multiple processes could have the same file open. In general, we don't force, it's not like only a single process can have a given file open at once. So one thing we're going to have is we're basically going to have a list of the number of processes that have that file open. Now, can anyone think of why we might want to keep that piece of information in this table? Why do we care about how many processes have this file open? Yes? That's true. So you could do things to try to prevent your file from getting corrupted by seeing that maybe multiple people are writing. So that's a good idea. But how about just from the perspective of maintaining this table of open files? Right, so basically every time a process is opening a file, you're basically adding an entry to this open file table. And if some other process opens the same file, right, that entry is already going to be there, so you're just going to increment the open count. So what's going to happen or rather, when is it that you actually delete something from the open process table? When is something no longer needed in the open process table? Yes, sorry, the open file table, sorry.
When no processes have it open.
Right, when no processes have it open, right? Because you could have multiple processes all accessing the same file, right? So when a process is done working with a file and closes it, essentially that file count is going to tell you when it's safe to remove that file from the table, because all the processes are sharing that one entry, right? So if you have 3 different processes, then you're going to have with the same file, you'll have an open count of 3, and it'll only be when all 3 of them have closed the file that you can actually release the entry from the table. Right? So then, other things that are going to be stored in the open file table are things like, the attributes of the file, who owns it, where the file is located on disk, and also we won't talk about this too much today, but the OS is often caching files in memory. So you'll also store a reference to where the file is actually sitting in memory. So that's the first main data structure, is this global open file table. But then you're also going to have a per process file table. So here you're basically going to have for every process you're going to have a list of files that process has open, and for that in that table for each open file by that specific process, you're of course going to have a pointer to the single entry for that file in the global table. But then you're also going to have things like the current position in the file, right? That's basically this file pointer. And other things like how the process is accessing a file. So internally, when a process basically says, I want to open this file, you have to specify the mode in which you're opening it. So you might say, I want to open this file, but just to read it. Open it in read-only mode, or open it in read and write mode. There are a few different possible modes. Now, why is this type of information not stored in the global table? Why do we want to have all of these tables on a per process level? So let's consider something like the current position in the file. Right, so we could have multiple, yes?
It'll be different for every process that has the file open.
Right. It'll be different, potentially, for every process that has that file open. Right, because all of this stuff here is essentially global to a file, regardless of how many processes are actually working with it. Right, but if this is our file, and we have two different processes that are working with this file, each process is going to have its own file pointer because they could be working on different parts of the file. Right? So something like the current position in the file is a piece of data that you need to maintain for every single process that's working with the file. You can't just keep one copy of it because then you wouldn't be able to handle multiple processes working with the same file. Questions on that? That makes sense? So one global table, and then per process tables that are storing state that is associated with a specific process as opposed to just the file as a whole. So now let's talk a little bit about how we actually do this. What happens when we're actually, say, creating a file, right? So when you're creating a file, you're basically saying, here's a file name. I want to create a file with this name. So largely what's going on here is a bunch of error checking. So the OS has to ask, do I have enough space on disk to create this file? Do you have permissions to create the file where you're trying to create it? And then assuming that all of those is fine, that you can actually create the file, you're basically going to create a file descriptor for the file, which is again going to allocate essentially an internal numeric ID that the OS is actually going to use to identify that file. And then you'll store where it's actually stored on disk and give it all of its file attributes. And one attribute that is sort of optional is what the file type is. Right, so like, is this a Word file? Is this an executable file? And there's essentially, this essentially is a choice we have to make is, do we want to store that in our file system? Right, so why might it be useful to store information like what the file type is with the file? Why might that be a useful piece of information to have? Yeah. Right. So that's the sort of the most reasonable thing is that when you say double click on a file in your OS, you double click on a file and it opens up, if it's a Word file, it opens up Microsoft Word. Well, how does it know that? Because there obviously is some information stored about what the file type is, what should I do when I want to work with that file, right? Because when you double click on a file, you're not saying, okay, I want to open Microsoft Word now, and then I want to open this file. Now, you could, of course, do that. You could, first open up Microsoft Word, and then inside Microsoft Word say open, go to this file, open it up. But in general, you're not doing that. You're basically letting your OS, figure out what it is you probably want to do when you want to work with that file. So, might there be any downside to doing it that way? Why might you not want to store, file type with each file? Yes. That's true. It might make it a problem if you want to later change the type of the file. How about, how many different possible file types might you have? Several. Well, potentially any number, right? I mean, if you might have a file type, every single, type of application, Microsoft Word or any other application that saves a file might have its own file type. Right, so you could have potentially a huge number of file types. And essentially, you're basically then going to say, well, my OS needs to know what to do with potentially every new type of file I add. Right, so that might be an issue. Advantages are it lets us do things like, have your OS know what to do when you want to double click on a file. But disadvantage is it's essentially making your file system more complicated, potentially less flexible to basically say up front that this file is this specific type. So, for example, in Unix, you essentially don't have file types. Every file is basically just a bunch of data, and the way you are explicitly using the file determines what's going to happen with it. right? So obviously, if you open up a text editor and then open up some specific file, it's assuming that it's, just a file that can be read by the text editor, right? But you can also do something like open up a text editor and then in your text editor open up some binary program file, and it will do that because it's essentially just assuming that you know what you're doing. It's just, yes, question?
So in Mac/Windows, like isn't the file type stuff all dealt with by the file suffix, or is there actually a
Yeah, good point. So oftentimes, right, when you name a file has some kind of suffix, right? So, if I make a text file, if I make a text file, I might call it, file.txt, right? And that sort of identifies it as a text file, right? But basically, this suffix is essentially just part of the file name, right? Like this is a useful convention that, I might do this, or I might have, for on Windows, I might have a program file that's called, program.exe, for example, right? That's a Windows executable file. But essentially, these are just parts of the program name, or parts of the file name, and you could change those to whatever you want. And in general, those are basically just being used as hints to the OS, right? So if you open up a file that has a .txt extension, the OS can say, well, probably that's a text file, but that's still not actually something that's being associated with the file itself within the file system. It's just part of that human-readable name that by convention is being used to say what it is.
So Mac and Windows still have a field for file attributes?
Yes. So actually, if we return to this, so for example here, see, we have this thing, this content creator. So when you're creating a file, it's essentially saying who created that file, and that is basically telling the machine what to do, like what program should be used to open it, right? So in this case, this is a PDF file, and so the content creator is this basically PDF utility. So, essentially we're storing the information with this file that if I click on that, I should open it up in a PDF viewer.
So like you just for kicks, if you rename that lecture14.txt, would it open? What would it open?
So that's actually, I actually don't know that off the top of my head.
Windows, I'm pretty sure it would just.
So the OS I know will basically warn you that you're trying to do something. So use txt. So this may actually open. So that did open actually in a text file, probably because this was actually leads to my follow-up thing, which is that in something like a Linux distribution, like if you're using Ubuntu and you double-click on a file, it's still opening up in general in whatever the application you expect. And the reason for that is essentially that the GUI is looking at the file extension and basically guessing what the type of the file is. And so essentially, it looks like what my machine here is essentially doing is saying that, well, you insisted that it was a TXT file, so I'm just going to believe you and open it up in a text editor. So essentially you can move this kind of functionality out of the file system into the GUI and just essentially do what was suggested. Look at the file extension, and sort of assume that that's what you want to open the file in.
So like we just assume that, or does this sort of lead us to believe that Windows and OS X are like phasing out the extra metadata because it needs to be or sort of a lazy thing?
Well, the metadata that's actually, essentially because it's already in there, it's not, it's extra information stored with files that presumably is, it's already been implemented. So I wouldn't imagine that it would be removed. But
Just like even though apparently it's not being used, so like it's not.
well, I think it is being used, at least. It essentially the GUI, it looks like, is just letting you override the information stored in it. So, deleting a file is, pretty straightforward. When you want to delete a file, you obviously need to, find the file, which is identified by the name you give it. So we'll talk a little bit about how we actually go about finding files. Now, of course, normally when you think of deleting a file, you're thinking, well, your file is stored on disk. I'm actually going to sort of, either wipe out or just free up that space. We're actually going to see that in some cases that's not actually going to happen using this notion of hard links, which we'll talk about in a minute. Now, when we're opening and closing a file, we're essentially operating on the file ID. So when you open up a file, you're basically getting back a file ID, which is the OS the actual identifier for that file. So when you open a file, we're again dealing with that system-wide open file table. Right? So when you open a file, you're first going to go into that file table, see if the file is already opened by some other process. If it's not, then you're actually going to take that file and copy it into the open file table. Of course, you'll do things like check whether you're allowed to access the file, increment the open count, and then for the process itself that's opening the file, you're of course going to make an entry in that per process file table for the file you're opening. And then close is pretty straightforward. We remove the entry from the per process table, decrement the open count, and then if the count is 0, that tells us no one is anymore using that particular file, so we can remove it from the system-wide table. So essentially all these are operating on file descriptors, which are basically just pointers to an actual file, which we'll see in a minute is not the same thing as the name that you may have given when you opened up the file. So when you want to basically read a file, we can basically consider two different ways of actually doing that. You can essentially do that either using random or direct access or sequential access. Right? So when you're doing random or direct access, this is basically saying, start at some point in the file and read some amount of data from that into some buffer that you give it. Right? So a pseudocode for what's happening is basically this. Now, obviously, your OS is, when it's actually reading a file, it's handing things off to the device driver to actually execute. But basically, you're just picking some piece of your file, reading it into a buffer. Now, with sequential access, you're essentially, again, using this idea of the file pointer, where you're not explicitly specifying, jump to this part in the file and read the data. You're basically just saying, wherever my file pointer is, I'm going to keep reading or writing sequentially. Right? So that's the idea of sequential access. And some types of file systems or I/O devices might actually only support sequential access and maybe not direct access. Right? So for example, if you have something like a tape drive, that's basically, which is often used as sort of a very long-term backup storage, that's a type of I/O device that's basically only designed for sequential access. You can't basically skip to any point in it. You're basically just reading the tape and reading or writing sequentially. Right, so with the sequential access pattern, that's where you're just reading or writing, starting at the file pointer, and then updating the file pointer when you're done, and then you'll continue reading or writing sequentially from there. Now, I should mention that all these types of calls that we're discussing are actually, the actual implementations of them are basically provided by whatever the specific file system you're using is. And so, a given system may have a whole bunch of different file systems implemented. So for example, in Linux, basically every single file system is implemented by a kernel module. So remember from way back when we were talking about, the modular approach to OS design, this is a good example of that, where basically, each file system type is stuck in a module. So what's some example of an actual file system? Can anyone think of any actual file system names? Yeah. Yeah, so NTFS is the file system most used on Windows. Yeah. Yeah, FAT is sort of a pretty old but commonly used one on things like flash drives. Yeah. Yes, I think there's several variants on many of these things. The most commonly used ones in Linux are either ext3 or ext4. Macs mostly use HFS. I mean, there's a whole bunch of different file systems that are basically all providing their own actual implementations, but they're all providing these same types of operations. So write's basically similar to read, so we don't need to belabor the point there. Seek I already mentioned. Yeah.
Is there a particular reason why file system types have been standardized?
Well, one reason is that file systems, just about any file system has some kind of limitations. And as is often the case, people designing file systems 20 years ago assumed that it would be good enough, and then it was wrong. So, for example, I don't remember my numbers may be off, but like, for example, the FAT file system is nice because it's essentially supported by just about every device on the planet and is really simple, but it also has, I don't know, I think it may be a 2 gigabyte file limit. Like, it can't store files larger than 2 gigabytes, and there are also limits on the size of the entire file system it can support. So, for example, an FAT system is often used on a little flash drive, because flash drives are not that big, but you're not going to have a 2 terabyte hard drive with an FAT file system. Right, so one reason is that everything gets bigger, so people keep coming out with new file systems, and of course that means that a given file system is usually not supported by every system out there. Right, so for example, NTFS is sort of Windows file system, but is not supported out of the box on a Mac, for example. Another thing that new file systems have tried to do is basically make them more resilient to corruption. Right, so for example, I mentioned ext3 and ext4, the file systems most used on Linux. There was also an ext2 and so on and so forth. And one of the things that they added somewhere along the way was basically this idea of journaling, which I won't get into, but essentially is a way to make your files less susceptible to corruption if your machine crashes. So, those kinds of things, people are always improving file systems, and then that leads inevitably to sort of a whole ecosystem of lots of different types of file systems, not all of which are universally supported. Other questions? Okay. So, seek I already mentioned, very simple idea. We're just going to take the file pointer and update it. Now, one thing to keep in mind there is that you can basically, a seek doesn't actually necessarily do any I/O, right? Because you're basically just updating this numeric pointer in memory, right? So you're not actually even potentially going to your disk to do that. And then we also have this idea of memory mapping, which we talked a little bit about many classes ago. This function mmap. But basically, the idea here is that one thing that you can do to make working with files much easier is to basically take your file or part of your file and map it directly onto an area of memory, right? So, if this is my memory space, and each of these is, various address in memory, I can basically say, I'm going to take this region of memory and I'm going to map that onto some file I have sitting on the disk. So if this is memory and this is a file on disk, I'm basically going to map this part of memory onto the disk. Yes, question?
So is that mapped from virtual memory or physical?
For virtual memory. Yeah, good point. Yeah, this is like the process's own virtual memory that it can directly access. This is all virtual. And so once I've memory mapped that file, you can basically just access this memory here like you normally would access any other piece of memory. But what that's actually doing is going to the disk and reading the file. Right, that makes it much easier because now you're not having to repeatedly call, open, close, read, write a million times. You just have this region that you can basically pretend like the file is sitting in memory. Now, of course, you don't have to actually read the whole thing into memory to begin with, but it's a nice, convenient abstraction when you want to potentially be working with a lot of different parts of a file without having to issue a ton of sort of the lower level I/O calls. Do you have a question?
Sort of. So for efficiency purposes, like now, as we know, the disk access is orders of magnitude slower.
Right, yes.
So is it the case at this point, because RAM is becoming so cheap, that programs haven't yet completely caught up in terms of being able to store an entire file in RAM in order to optimize speed?
So basically caching files in RAM is a very is a very common thing that OSs do, and especially as we have so much memory increasingly, that's much more of a useful optimization. So that's definitely, we're not basically going to be talking about caching today, but that is something that happens very, very often. And actually on a, I don't know that it's actually, I don't think it's a command on a Mac, but on a Linux machine, if you run the free command, which basically tells you how much memory your machine has free, it will basically break that down into how much memory your programs are using, and then how much memory you're not using but is basically being used to cache files, right? And so that's sort of less, that's not memory that's used, because of course a program can take it over if needed, but Linux will essentially use almost all of your available memory to cache files that's not being actively used by programs. Yes?
I guess in addition to that, so like this computer has 16 gigs of RAM.
Yeah.
But at most times only like 1/3 of that being used is like why is that?
I mean, do you know that the rest is that a lot is not actually being used to cache files? Because it may be.
So
I don't know like
just
what the.
just said-
I know offhand that the the free command in Linux does break that down. For a I assume your machine's running Windows. I don't know like what the system you monitor is showing, but there may be more file caching going on than it actually says. Question?
So that says 2.2 in use and then 2.4 gigs in cache.
Yeah, so that's probably referring to the file caches that your system's keeping. So, other questions before we move on? Okay. So we already talked a little bit about this, but essentially the two main ways that we can actually go about accessing a file are sequential access and direct access. Right, so sequential access is when we are processing data in order, 1 byte at a time. And actually most programs are basically accessing data sequentially. Right, so when you open up a text editor or a word processor and you open up a document, it basically is just taking your whole file, reading it sequentially into memory, and now you're going to be working with it. Right, that's not actually, it's not like you click your cursor on the second page of your document and all of a sudden it goes to the disk and pulls up the second, right, it read your whole file into memory to begin with. Right, so, and anything like, a compiler reading a source file is doing the same thing, reading it all sequentially and then processing the data after it's been read. Now, direct access is where we're not doing it sequentially. We are addressing a block of the file based on basically a key value. So a good example of a type of application that would do this is something like a database, where the pattern of access in a database, a database is typically huge, maybe hundreds of gigabytes. You're of course not reading a database sequentially. The access pattern is essentially requesting potentially random pieces of the database all over the place. So the access pattern there is clearly not sequential. And something like a hash table would be the same, right? Because every time you look up something in a hash table, based on the value of the hash, which is effectively random, you could be pulling data out of some random part of your hash table. Right, so that would be another example where you're basically doing direct access as opposed to sequential. And so the OS is essentially has the same issue of, can I address files sequentially or directly? And we already talked about when you're doing it sequentially, you're basically just keeping a pointer that you're updating every time you're doing a read or a write, whereas with direct you're specifying some position where you go to immediately. Question?
Just kind of clarify the direct. So you have blocks of data.
Yeah.
And you can access the blocks.
Yeah, direct is basically just it's random access. Right. That's basically what we mean by random access. Right. So when we say RAM, memory, random access memory, that's basically just this idea that you can immediately go to any piece of memory you want and access it directly. Right. That's what we mean by random access. So direct is the term used in the book, direct access, but essentially random access or direct access is essentially the same thing. So one important thing to note is that the access method is very important with respect to the performance of your disk, right? And also how things are laid out how your files are laid out on disk, right? Because you might imagine that depending on how things are laid out, it might be very, very slow to access things, access things in a random access fashion versus reading something sequentially. Right, so we'll talk more about that later, but essentially the access method is very important when we're talking about performance. Okay, so now let's talk about naming. So, question here is, how are we actually naming files? Right, because this is basically the main way that we use to we store things on disk with a name, and then when we get them back off the disk, we're doing that using a name, right? The OS itself may be using some, unique identifier, which may be just sort of some, arbitrary integer, for example. But when we want a file, we don't have any idea what that integer is. We know what the file name is, right? So, the OS is using numbers, but users, of course, are preferring textual names. Right, so basically what the OS is using to do this is a directory. Right, so a directory is, again, a term that we sort of all use every day. But directory, what a directory actually is it's basically an OS data structure that is mapping names to their actual files. Right, so the basic view of a directory is, it's a bunch of entries with file names. So this is food, this is bar, this is Baz, so on and so forth, and these are basically all just pointing to actual files on disk, or rather pointing to all of the metadata associated with a file, which also says where the data is actually located on disk, right? But essentially, this is a directory is like a lookup table from a file name to the actual file, data structure that the OS is maintaining. So, we have to consider, well, how are we actually going to lay out our directories? So, the simplest possible way is basically a single level directory, which is, essentially one huge directory that stores all of the files, right? So every single file sits in one directory. Now, what's the obvious downside to doing it that way? Yes. No organization. So that may be true. I mean, you could still sort of name your files, sort of arbitrarily long if you wanted to impose some organization that way. But yeah, it's true that essentially it's not imposing sort of any kind of organizational approach. What's an issue with regards to having multiple users, right? Because typically you may have 100 different users using the same file system, right? So yeah.
Not clear to users which files they have permission to access.
That's true. Yeah, it may not be clear which files you have permission to access, and that's getting at the point I was getting at, which is essentially that. What happens if you have two users who want to name their file the same thing? Right? What if you have report.txt and someone else wants to use report.txt? You essentially can't, because you can't have two files with the same name when you just have this one directory. Right? So you essentially, if one user uses a particular name, no one else is going to be able to use the same name. So this approach was used by some early computers, but another reason why that might be okay a long time ago is if you have a really small disk with not very many files, maybe that's all right. On today's machines, you have huge numbers of files, so clearly you don't want to be storing them all in a single level directory. So one way to make this a little bit nicer is to use a two-level directory where rather than just one directory, we'll have a directory for every single user. So, user A, user B, user C, and each of these are going to refer to a second level directory, and this is all of user A's files. This is the directory for user C and user B and then user C, and so on and so forth. Right, same basic idea, we're just now saying that the main directory is just going to have one entry for each user, and then each user will have its own second level directory that actually has their own files. Right, so that addresses some of the issues we said. Now you can reuse the same file name for each user. It's clearer what are your own files. It gives you some degree of organization. Still pretty restrictive, of course. Now actually we can... Let's just take a quick look. So, let's see. So here I'm just creating a few files, A, B, and C. So this is some directory I'm in, and we can actually see here the actual file identifiers that the OS is creating. right? So when you say ls-i, that's basically saying, show me the actual internal identifiers that are being created, which are these numbers here. So these numbers, these long numbers are the actual identifiers that the OS is using to identify the file. So, but actually, in general, we don't use a two-level directory either. What actual modern systems use is sort of a multi-level directory where you can have any number of levels, where it's essentially a tree structure, right? So when you think about the directory structure of your actual machine, right, what you typically have is some root directory, just going to be a slash on Linux, where you have things like slash user, slash bin, slash home, so on and so forth. And each of these are pointing to another directory. So slash home is normally where we keep user home directories. So here we might have user A, user B, user C, and then so on and so forth. They all have their own directories, and we essentially don't impose any kind of a limit on the number of levels, right? So this is basically just a tree structure, right, where we have lots of levels, and then down at the bottom, if we have, down at the bottom we have the actual files, which are, once you get to the end of your directory tree, you have an actual file, right? And that's how we actually specify file names in modern systems. You have slash user, slash bin, slash whatever, and you ultimately get down to the file name, and that determines the actual file and the set of directories. So basically a directory in this context, essentially a directory is just another type of a file, right? Because in a given directory, you can have other directories, and basically all a directory is a special type of file that points to another directory, right? But that's basically how you're, when you say ls, you're in some directory and you say ls, and you see a bunch of files, some of which are directories, but you're essentially sort of treating them equally. Directories are simply, pointing to, another directory table. So now when we actually are looking up a file in this scheme, obviously this is a little bit more expensive because we are potentially doing multiple directory traversals, right? Because if you say slash home slash a slash this is another directory down here of user A's files, and maybe we have some file file.txt, right? And then that is actually pointing to the file itself. Right, so if I have slash home slash a file.txt, then in order to look up that name, you obviously are starting from the root directory, you find the home directory, find the user A directory, and then file.txt, and that points to the actual file you're looking for. Now, there are still some limitations with this sort of basic tree structure. And one is that it's kind of difficult to share. What if we wanted to share a file either across multiple directories or users, right? So why might that be maybe difficult? Why might that be difficult to share files if we're using this basic tree structure? Yeah. Right, essentially because you're going down some directory tree to find a file, and if I want user A and user C to be sharing this file, well, that might be difficult, especially because user A is probably restricting his own directory to access by user A, right? Other users probably don't want to be, you probably don't want to let other people access your home directory, but you might have a file somewhere in your home directory that maybe you would like to be shared with some other users, right? And so that might be actually difficult to do this. And another issue is, it might be the case that, well, maybe you actually want to have multiple file names pointing to the same file, right? Because again, the file name is just basically a lookup identifier for the actual piece of data on the disk, right? So there's no inherent reason why it seems like you shouldn't be able to have multiple file names that refer to the same piece of data. So we actually can do this using this idea of links. So basically, so far we've essentially been assuming that each file has a unique name, but in general that doesn't actually need to be the case. So we basically have this idea of hard links, and so we'll talk about this using how it's done in Unix. But basically, you have this ln command, which stands for link, and it lets you basically create a new hard link that refers to some file. And basically what that's doing is it's creating another file, but it's going to refer to the same piece of data that's already there. Right, so if I have some file and it's named A, and that's pointing to an actual file, like an OS file object, right? So that would be like this, file.txt is pointing to this actual OS file object. And I say, ln_ab, what that's saying is I want to create a new hard link to the file A, and I'm going to call my new hard link file, I'm going to call my quote, new file B. So now what we have is we have, of course, the original file A pointing to the same file with, maybe the file has an ID of 100. That just might be the internal identifier. And now we have another file B that points to exactly the same. So, right, so if I could have, file 2, maybe I create file2.txt, and that's a hard link to the same file. Right, so it looks like two different file names, but pointing to the same data. So let's actually look at a quick example of that. So, I'm in here and I have my three, files A, B, and C. And let's say I want to create a new hard link to A, and let's say I want to name that A2. So now let's look at that, and we see that, right, so here's A2, so there's A and A2, and we see that the internal identifiers for those files are the same. Right, so this looks like two files, from the perspective of the file system, it looks like two separate files, but they are referring to the same piece of data on the disk. Right, so let's say I go into file A2, for example. Let's say, this is some text. Let's save that. And now we see that, the size of file A2 went from 0 bytes up to 18 bytes, and the same happened to file A. Right? We were editing file A2, but if we, show both of them, right, we're clearly editing the same actual piece of data. Yeah.
What happens if you have A2 open and you try to open A, will it reject it consecutively?
Well, so that would be, remember, we already said that we could have the same file open multiple times. Right? You could have multiple programs open the same file. Now, oftentimes, I think what you might be thinking of is that programs will often do things like warn you if you open a file that's already open. And that's basically just because they are seeing that some other program has it open and are guessing that maybe you don't want to do that. But they will still let you. Right? The OS is not imposing any restriction that you can't have multiple processes opening the same file and working on it. But programs themselves, like if you have a text editor and you take two copies of the text editor and try to open the same file, normally the second one will yell at you and say, the file is open. Are you sure you want to open the file again? Does that answer your question?
Yeah.
Question? Yes.
So what happens if you kind of edit something in one process, save it, where the process has it?
Well, then it's entirely possible you basically will corrupt the file. Because when you're actually editing a file in a text editor, again, what's happening is you're not actually editing the file on the disk. You have a copy in memory of the file that you're editing it, and then when you actually save it, it writes it out to the disk. So typically what would happen if you opened up the same file in two text editors and you were editing them in both copies, then you save the first one, it will write it to disk. Nothing will happen in the second copy because you're still working in, the in-memory version. Now, it's possible that if you maybe waited a little while, the second editor might detect that the disk version has changed and will say, do you want to load the most recent version of the file? But essentially, that's all application dependent as to, how you want to handle that. The OS will just, all the file system is doing is taking reads and writes and applying them to the file, right? So, it doesn't really care if they're coming from the same process or multiple processes. It can still, do those operations. Other questions? So So the other thing here is that now that we have multiple hard links, we have this. We're going to add this idea of a reference count, which basically says for a given file, how many file names are actually pointing to this file, right? So for example, if we have these two file and file2.txt are both pointing to the same file, then this file here is going to have a reference count of 2. And we can actually see that up here. So this number right here is actually showing the reference count, right? So this is saying right here that files B and C, there's only one file name actually pointing to those. But A and A2, there's actually 2 files pointing to those, right? And we can see that, if we create another hard link, so let's say we create, A3, or let's say we create a hard link to A and call it A3, now we see that, the reference count has been increased to 3. So why do we need this reference count now? Why might this reference count be useful? Yes? Right, if you're attempting to delete a file, right? So right now, the contents of A1, A2, and A3 are all, this is some text. Now if I say, RMA2, what should that do? Right, if I'm deleting A2, usually we think, well, this is going to wipe out the file. But all that's actually doing is sort of deleting basically A2, which is sort of a reference to that piece of data, right? So if I delete that, and now let's see, right, so there's A and A3 are still there, right? That didn't actually do anything to the underlying data. It deleted A2 and decreased the reference count, but the actual file was not affected. Yes, question?
You'd actually deleted A where you deleted the other references since that was...
No, because, right, so the name A or A2 or A3 are just names, right? When you're saying a hard link to A, all you're really saying is a hard link to the file represented by A, right? So I could still delete A, and A3 is still going to be there, and the data is still going to be intact. Right, because essentially all the files are all equal. They're all just pointing to the same piece of data. And when I say lna, all I'm basically saying is I'm using A to point to the actual file that I'm hard linking. Right, the actual name that I'm using is sort of immaterial. It's just the actual file that A refers to. Other questions on that? So there is one problem with hard linking, which is, suppose that I hard link some directory, right? So suppose that C here is actually a hard link to, so what hard linking is basically doing is it allows us to, if I have in user C, maybe I have a file here, file.txt, I can actually hard link that to this file. And remember, this is basically getting around the issue we said of making it easy to say share files, right? Because now I basically have a file that is essentially traversing the tree structure, right? So this is actually no longer a tree when we introduce hard links. It's now what we basically call a directed acyclic graph. But if we allow ourselves to say hard link directories, then we could end up with something like this, where what if I take this and say, hard link it to, the root directory? Then now essentially what we have is we have a cycle where we have /home/c/home/c/ so on and so forth. You essentially have a cycle there, and that's a major problem if you want to do something like back up your file system or search your file system. I mean, sort of the easiest way that you would think to search the file system is to basically, check every single directory entry, and then within each directory entry, check every further directory entry, right? Essentially traversing it hierarchically. And if you have a cycle, you're going to get stuck in an infinite loop doing that, right? So basically, that is a problem that essentially is just addressed by saying we don't let you hard link a directory. Right, and so that's basically exactly what we will see here. If I make some directory, testdir, and then try to hard link, it won't let you. It's going to say that's a directory, right? And so the whole point is we don't want to have these cycles. It's okay with files because files are always essentially the end of the tree, right? A file never leads to anything else. That is the end. But because a directory could create a cycle, we don't want that. Yes?
What's the difference between hard links and symbolic links?
Next slide. So, yeah, so that's essentially the solution here. But this is not. Maybe we would like to be able to link to directories, for example. So this is where we have also the idea of soft links or symbolic links. So we essentially can use the same idea here, but basically the difference here is that rather than pointing to the actual file, the link is going to point just to the name, right? So this is basically a name alias. So now, using the same example, file name A is pointing to some file, file ID 100. And now when we say ln, well, there should be an ln-s here, but assuming this is a soft link, then we create B, which is not pointing to file 100, it's now just pointing to the file name A. So now when we access that, it doesn't immediately tell us the file we're looking for. It is basically just saying, use this as an alias for some other name. Yes?
So this essentially are Windows shortcuts, basically?
Yes. So this is basically Windows shortcuts. Mac OS aliases are basically soft links as well. And so the point here is that they are not referring to the same actual file. It's just essentially a name forwarding. So, in this example, if we removed A, for example, if we deleted the file A, then the file is actually gone because the file B is simply a soft link to A, and file A is no longer there. So let's look at a quick example of that. So, here we have our remaining files, and now let's say I want to make a soft link to, let's say, A3, and we'll call that soft. So here is that soft link I just created. And first we see that the reference count of A3 did not get updated, right? Because there's still just the one file that actually refers to this file. But now we have this soft link, which is basically saying when I use that file, just do a second name lookup for A3. So if I do cat ssoft, it still is going to show the expected text, but all it's actually doing is looking up A3. Yes?
Why is the reference count on test directory of 2?
Yes, the question was, why is this directory have a reference count of 2? And that is actually because if you look in any directory, right, we have, even an empty directory has basically 2 files. 1 dot is the current directory, and 2 dots is the parent directory, and those are actually hard links, right? So this is actually a hard link to the parent directory. So that answers your question. So every single directory basically has a hard link from within itself, essentially. Do you have a question?
Yeah, what happens if you blow away
I'm quite sure it won't let you, but I don't know what the error is. Yeah. So right, those are basically right, because this is actually the one exception to the rule: you cannot hard link a directory. I'm sure. Oh, 3 dots. What did I just blow away? I'm not sure what I just blew away. But in any case, so what you want rm-f. Well, no, that actually won't do. That will blow away the directory you're in, right? Because that will just go to the parent directory. So it will work. It will work, right? Because it's referring to the parent directory. That's exactly what we use 2 dots for.
So if you did it with 1 dot, right?
So if you did rm and 1 dot, that would just try to delete the current directory. I think so, yeah. But so in any case, to just quickly return to the soft links here. So now if we say delete A3, right? So we just saw that, if we say cat soft, it does show the text that's in A3. But now note that the file sizes of this are different, right? Because in the previous case with hard links, each file was essentially indistinguishable, right? In this case, A3 is the actual data, which is, 18 bytes. And, I can make that longer. And now it's 108 bytes, but the soft link is just an alias, right? There's basically no data there other than saying, do a name lookup to this other file. So I can go ahead and actually delete A3. And now if I try to do that, it's going to say no such file or directory, right? Because it's still there, it's still pointing to A3, but A3 is missing. So, obviously a good question is, well, why do we have both hard and soft links? Right, so, yes.
I was just going to say that at least on Windows, you can't make hard links across this.
Yes, so that's true. You can't, one disadvantage, basically soft links are very, very flexible. You can do a soft link to another directory, right? Because all that's basically saying is look up this other name. But, it's essentially just it's essentially treated as a special type of file. So if you try to back up the directory that has a soft link to somewhere else, it will just copy that soft link, which will probably end up referring to a file name that's no longer there, but it will just copy that alias for you. So you have that flexibility that you don't have with hard links. But what's a disadvantage of using soft links? So we just saw one disadvantage, right? What happened when I blow away R3? What happened to the soft link? Yeah. Right. Essentially, you can end up with dead links that point to files that have either been deleted or are no longer there, right? Because I could also move that soft link to somewhere else where there might not even be an A3 file in the directory anymore, in which case it's, again, sort of a broken link. How about, and this is a minor issue, but also, how about the speed of accessing a hard link versus a soft link? So what do you have to do when you access a soft link? What? Sorry, I can't hear. Yeah, a hard link is going to be a little bit faster because on a soft link, you're looking up another name. Yes?
Soft link run into any issues when you file?
Right, the soft link basically knows nothing about the file it's actually pointing to, and if you can either move the original file or delete it, and the soft link is just going to sit there. So that's, again, the downside is that soft links can very easily get broken. Yes.
So you can soft link to soft link.
I think you can soft link to a soft link, yeah. Yeah, I mean, a soft link is very, very conceptually simple. All it is it's saying when you use this file, forward it to this other file name. And that file name could be completely invalid because it doesn't know anything about what that file name actually means. It's just some other file name. It's essentially just a forwarding address, basically, yes.
Soft link allows you to get the same directory as,
No, you can soft link to something all the way, anywhere in your file system. I could say, soft link to /user/ whatever, really long file, that's fine. Okay, so we're out of time, so we're going to have to pick this up next time. Remember that the third homework is due on Monday, and exam is 2 weeks from today.